Today, I'm going to feature the resistive and capacitive series circuit. You'll see in front of you that I have an AC power supply with a value of 115 volts AC. I've got a resistor, 63.1 ohms resistance, and in series with it, I've got this capacitor at 25 microfarads. I've got all of the values that are listed here, but we've got quite a few that are missing. And so I'm going to take you through the procedure and how to solve for all of the missing values. The first thing that we're going to start with, because of the fact I only have a value of capacitance, my first order of business in solving for this is establishing a value for capacitive reactance. So let's move down to the next board and get started. Here, our first step is going to be to determine the value of capacitive reactance using the following formula. Capacitance is equal to 1 over 2 multiplied by the value of pi times the frequency times the value of capacitive reactance. Well, here I'm looking for capacitive reactance, so we're going to have to modify this formula, and it's quite easy. We're just going to substitute the XC for C, and we're just going to switch them up. So that formula is going to be rewritten in the following format. X sub C will be equal to 2 times pi times frequency times C 1 over. Well, let's put in our values. Two times 3.1416. Now these are constants. Our frequency, which, by the way, I did not mention it, is 60 hertz. It's a North American standard. And then we're going to multiply it by our value of capacitance, which in this case was 25 microfarads. So 25 microfarads. This formula works off of the base unit of capacitance. If this is listed in microfarads, I have to adjust and account for that in the calculation. Now, normally, you would just divide it by a million, and then I gotta grab my ruler. This is a long formula. Now, remembering that if you're going to be punching this into a calculator, the PEDMAS rules, this would have to be done in brackets. Otherwise, you're going to get a much different answer. There's also a little trick to this. Because of the fact that we're working with a value of 60 hertz, which is pretty much standard, we could take a shortcut. The constant here is 377 multiplied by the 25 microfarads, which we're going to divide by a million in order to get it into the base unit of farads, and 1 over. Putting this into a calculator, done properly, following all the PEDMAS rules, a person should get the following answer. 106.1 ohms of capacitive reactance. Capacitive reactance, much like inductive reactance, is a unit of measure that is measured in ohms because it has the same type of qualities as resistance, as it acts to control the amount of current flow in a circuit. Now that I have calculated the value of capacitive reactance, I now have two values that will allow me to calculate for the value of circuit impedance, or Z. Once I have circuit impedance, I can now determine the current because I'll have two values for the entire circuit. So that's going to be our step 2. We're going to calculate the value of circuit impedance. Let's move back down that way. Okay. Step 2, calculating circuit impedance. This is the same formula we've used previously in other circuits, where we're going to take the value of resistance squared plus the value of capacitive reactance squared, square root. Using the values that we've calculated previously and the given value of resistance, we're going to input that information. Z will be equal to the value of 63.1 ohms of resistance squared plus 106.1 ohms squared of capacitive reactance, square root, and then punching all of this into a calculator, you are going to get, oddly enough, 123.45 ohms of impedance. Now, this is a value that was rounded to 2 decimal places. It was actually a 123.447 and so on, and it was rounded up to 4 or 5. Well, now that I've got the impedance, as I said previously, I'll now have 2 values for the entire circuit. That's going to unlock me being able to calculate the entire current draw for the circuit. So that's going to be our step 3. So I'm going to erase the board and we're going to just keep cracking on. So here we have step 3, calculating the current draw for the entire circuit. We're going to use an Ohm's law formula, which is I total is we're going to take the applied voltage and we're going to divide it by the value of impedance, which we've just calculated. We're going to input our values, 115 volts, divided by 123.45 ohms, giving us as an answer 0.932 amperes. Now normally we advocate to round to 2 decimal places, but because of the fact that I'm dealing with current that's below 1 amp, I felt it was necessary to go to 3 decimal places in order to maintain a high degree of accuracy. So for the purposes of this demonstration, with the current, I'm actually going to 3 decimal places of accuracy because of the fact it's such a low value. Now that I've got step 3 done, the current draw, that allows me to unlock the rest of the circuit. So let's go down and look at the circuit and I'll explain it a little bit more in detail. Now that we've calculated the value of current for the entire circuit, due to the fact that this is a series circuit, and one of the properties of a series circuit is that the current draw of the circuit, the current will be the same at any point in the circuit. Meaning, I could take this value now and transpose it and add it to the missing values across the resistive component and across the capacitive component. Now that I've got 2 values, I can go ahead and now solve for the remaining missing values for this resistive component, which is what I'm going to do next. I'm going to find the value of the voltage drop across the resistor. Using that value, I'm also going to use it with the current to calculate the value of true power. So let's keep moving down. Here we are at step 4, calculating the voltage drop across the resistor. We're using simply Ohm's law, where we're going to find the voltage drop by taking the value of current and we're going to multiply that by the value of resistance. Our current was calculated at 0.932 amperes multiplied by the value of resistance, in this case 63.1 ohms. Punching this into a calculator, you should be getting, as a result, 58.81 volts AC. Again, rounded to 2 decimal places. Now that I have this, I can use this value and proceed to step 5, which was, as we mentioned previously, calculate the amount of true power that resistor is consuming. Pardon me. Our value of the voltage drop, 58.81 volts. AC multiplied by 0.932 amperes. The power consumed by the resistor is going to be 54.81 watts. Now, I'm going to take a second. I'm going to go and input this in the chart, and we're going to discuss what are our strategies moving forward onto steps 6. Now that I've finished adding these two values into our chart, we can see that the resistive component is complete. I now have to finish the missing values for the capacitive component, specifically the voltage drop, as well as find a value for the reactive power that this capacitor is going to generate. So let's get back down there and finish these calculations. Step 6, calculating the voltage drop across the capacitor. Again, we're using Ohm's law. We're going to determine this by taking the value of current we've calculated and multiplying it by the value of capacitive reactance. The values are 0.932 amperes multiplied by 106.1 ohms, giving us 98.89 volts AC. Now that I've got a voltage drop, it's a simple matter now of proceeding to step 7 and calculating the amount of reactive power a capacitor is going to generate. Using Ohm's law, the only thing we've done is we've substituted the P for the value of var C. It is still considered to be power. We still calculate it in the same manner. We'll take the voltage drop, 98.89 volts, multiplied by the current, 0.932 amperes, giving us 107.23 VARs, volt amps reactive for the capacitor. I'm going to move down and I'm going to input these into our chart. Now that I've marked down the values of the voltage drop and of the reactive power, we can now go back and solve for the remaining values for the entire circuit, specifically the V8 or the apparent power. I will use the value of power and the value of var C, or power from the capacitor, in order to calculate for the V8. Once I have that, then we'll proceed to calculating power factor and finally angle theta. Here we have step number 8. determining the amount of apparent power that this circuit is going to consume. Now, we are going to be using a trig formula. We're going to be using the value of power squared plus the value of reactive power squared, the square root. Now, I'm going to input the values that we've calculated. 54.81 watts squared plus 92.17 vars C squared square root, and as a result, punching this into a calculator, you should be getting 107.23 volt amps, VA. Next, we're going to move on to power factor. I'm just going to kind of move down the board here so I can make myself some room. On to step 9, finding the efficiency of the circuit, or in other words, power factor. Now, there are many formulas that can be used to determine power factor. However, I've always used power factor is equal to P over VA because it's easy for me to remember. This power factor, this formula is the ratio of true power to apparent power. Working from power, I always use the same formula, and it does not change whether or not I'm working with a series circuit, a parallel circuit, or a combination circuit. If we start using values of voltage, it changes because I'm working with a series circuit. If I was working with a parallel circuit, that formula wouldn't function. I'd have to use the current draw of each of the branches. And so in order to keep things simple, I've always worked from power. Now, that being said, let's put in our values. 54.81 watts divided by 107.23 VA. And that's going to give us 0.5111. Now, power factor is usually expressed as a percentage, and so I would have to take this value and multiply it by 100, giving me for an answer 51.11%. Now, all that remains is to determine angle theta. Now, in the textbooks, they'll give you the simple formula, cosine of angle theta is equal to power factor. What we have to do is use the value of power factor as it came out of our calculator. And this has to be manipulated in order to isolate angle theta. So angle theta is actually equal to the power factor multiplied, or we use the minus cosine function in our calculator. So it becomes a simple matter of using 0.5111 and punching in the negative cosine. Now, we calculate angle theta in this procedure right after power factor because more than likely you've still got that value in your calculator, and it simply becomes a matter of just pushing in second function, negative cosine, and there's your answer. So, incidentally, what's angle theta? It works out to be 59.25 degrees of phase angle difference between the voltage and the current. Now, we're going to move on. I will input all of this into the chart, and then we're going to talk about how to chart and draw out the voltage and current values for the entire circuit. Now, what we're going to do is we're going to chart or explain at what point in the circuit are the relationships between the voltage and current waveform, specifically across the resistive component, across the capacitive component, and then across or coming from the power supply. So I'm going to set something up on the board and we'll be right back. Now, discussing the voltage and current relationship as it relates to an RC, or resistive and capacitive series circuit, I've taken the liberty of drawing in the current waveform. One of the characteristics of the series circuit is the current is the same at any point in the circuit. It wouldn't matter where I measured it in terms of with an oscilloscope. That current waveform would always show up in the exact same location on my oscilloscope graph. So that's why I've drawn it out. Now, R represents the resistive load module. Now, the voltage waveform, it is said that voltage and current are in phase with one another in a purely resistive circuit. So when we draw this out, that means, and I'm going to use blue to represent the voltage waveform, that when they start at the zero, at the time base, they both will start at the exact same location. They will rise and peak in unison and collapse in unison, crossing over at the zero time baseline, going into the negative alternation, and continuing the same trend. Obviously, you're going to want to identify this if you are working with the same, like a pencil. I've got colored markers. We're also going to draw it out or explain that voltage and current are in phase with each other, and that angle theta would be equal to 0 degrees. Because what we don't see is any kind of phase angle difference at this line between the voltage and current. Now we're going to proceed to doing the same thing, but across the capacitive load module. So I'll be right back. Now we're looking at what would be the voltage and current relationship across the capacitive load module, identified by the X sub C, which stands for capacitive reactance. Capacitors are known for resisting or opposing a change of voltage. Now, when we have a series circuit where the current is a fixed value, current can't lead or lag anything. It's fixed. So the voltage, because of the fact that the capacitors oppose a change of voltage, that means then that there's going to be a phase angle difference with the voltage either leading or lagging. In a textbook, they will stipulate that the voltage lags behind the current in a purely capacitive circuit by 90 degrees. Now, when we look at it, this represents a full 360 degrees. In the middle, 180. Here is your 90 degrees. Now, if the voltage is lagging, that means then that when the current waveform is at 0, the voltage will be at its peak, but in the negative alternation. When the current is at its peak, the voltage will be at 0. And so this is how I'm going to have to draw it in. Now, this is about half here. That'll stand up for 270 degrees. So I'm going to start about here, cross at 90, peak at 180, collapse, cross over at 270, and continue the trend. Well, that's a little bit sloppy, but I think we get the general idea. We're going to identify it, and we're also going to spell it out. I'm just going to move the camera a little bit so we can actually catch. Voltage lags the current by 90 degrees in a series circuit. It is important that we put down context, meaning why does the voltage lag behind the current? It's because it is a series circuit. Conversely, could voltage lag behind current in a parallel circuit? No, because the opposite is true, that in a parallel circuit, the voltage waveform is fixed. It is stationary, and is the current waveform that either leads or lags. So it's really important that we pay attention to the logic, the context, and that things are grammatically correct. Now, we've done this. I'm going to move on to drawing this out for the entire circuit. So I'll be right back. Here we have our final graph. Z represents the entire circuit. I've got, again, my current waveform drawn in the exact same location. This time, I've added a piece of information. Angle theta. In our previous calculations, we calculated that angle theta for this circuit came up at about 59 degrees, more or less. For me to be able to draw my voltage waveform, I need to be able to dissect this. We know that this is full 360 degrees. In the middle, 270, 180, and right about here, I'm going to use my ruler. And so actually, right about here would be 90. And if I was to break this up into 3 equal parts, there and there, in the same distance, this right here would represent 60 degrees roughly. Same thing over here. Because I need to maintain that phase angle difference. And that my peak, so 60 degrees, my peak is going to be right in the middle, right about there. Capacitors oppose a change of voltage, and how that affects the voltage and current relationship is that the voltage is going to lag behind the current waveform. If the current waveform is at 0, then that means that my voltage is going to be in its negative alternation. Now, if I draw this out, that means then that I'm going to be something like this, and at 60 degrees phase angle difference with the voltage lagging, I'm going to peak about here, come down, cross over at the same distance from the voltage waveform, and kind of continue on in the same trend. I'm going to identify that waveform, and I'm going to write it out that, switch colors. Voltage lags behind the current by angle theta, which is equal, in this case, to 59.26 degrees in a series circuit. We need to put down this information because it is grammatically correct and it is logical. The current waveform, it's stationary. It can't lead, it cannot lag. The voltage waveform must change in relation to the stationary current waveform. Some people tend to argue, I'm saying the exact same thing. No, you're not, unfortunately. So this is the most correct way of doing it. I hope you found this informative. I'm hoping that this helps clarify things that you might be reading in textbooks. And please subscribe and tune in to other videos that we are producing here, such as the RC parallel circuit. So until next time, please stay safe.